Okay. Hello students. Welcome to this new video on heat exchanger analysis. So basically in this video we will be talking about, we'll try to understand how the design of heat exchanger is being performed. So especially in this video we'll try to understand what is logarithmic mean temperature difference, that is LMTD. Why, in what way this LMTD is important and why we have to know it. So we shall try to throw some light on all these things. Now basically, as we saw about the introduction about heat exchanger in the last class, that is last video. So basically what is going to happen, so you have a heat exchanger where there is this hot fluid which will be moving. So I will be marking it like this. There is a hot fluid which will be moving, and also there will be a cold fluid which will be moving. So let us write this. This is a hot fluid and this is a cold fluid. So this hot fluid, it will be entering at, we shall use the notation as TH1, which denotes as the inlet temperature for hot fluid, and this is TC1, that is inlet temperature of the cold fluid, and similarly TH2 and TC2, which is outlet temperatures of hot and cold fluid. So basically if you see here, there are two ways by which heat exchanger can be designed. First thing is, if we know, when we know about inlet and outlet temperatures of the fluids, inlet and outlet temperatures of both the fluids, so of both the fluids means both hot and cold fluids. So if you know TH1, TC1, TH2, at least minimum 3 temperatures we need to know. So the other temperatures, so basically 4 temperatures we need to know. For that given 4 temperatures, we can decide upon what is the area required, what is the length of the heat exchanger. Okay, so all these parameters can be decided based on these 4 parameters. So that is one way. And second way is, already a heat exchanger is there. Suppose say you know the length of the heat exchanger, or if a customer comes and tells you that I have a space, allocated space, within that space I want you to design the heat exchanger. So L is fixed or area is fixed, and for that you are supposed to find out what is the temperatures, available temperatures, what are the temperatures that can be obtained, temperatures to be found. So basically these are the two situations we can come across when we are going for the design of heat exchangers. So now this is where the thing called LMTD arises. That is, when you know all the 4 temperatures, then we will go for LMTD analysis, that is logarithmic mean temperature difference method. And when you don't know all the 4 temperatures, you know something other details about the heat exchanger only if you know certain other details, not the temperatures, or only a partly you know that information about the hot and cold fluid, that is the temperature data, only partly you know, not completely, then you will go for what is method called as NTU method, or which is called as effectiveness method. So these are the two methods which we are going to learn. These are two popular methods which usually people use when they want to design any heat exchanger. Okay, now let us try to understand what is this LMTD, that is logarithmic mean temperature difference, and how do we define LMTD. So the first thing is definition of LMTD. So from now onwards, I will be only using LMTD abbreviation. So logarithmic mean temperature difference. So this is our first goal. First, we need to define what is LMTD, and second thing is we have to find out the derivation or expression. We have to find out the expression of LMTD for parallel and counterflow heat exchanger. Okay, parallel and counterflow heat exchanger. So this is our goal as far as LMTD is concerned. So if we know how to find out, if we know how to define LMTD, and if we know how to derive the expression, so derive an expression. So please make correction here. Derive an expression for LMTD. Derive an expression of LMTD for parallel and counterflow heat exchanger. So this is the first part, wherein which afterwards we will try to do problems on LMTD approach. Okay, these are our goals. Now let us try to define what actually LMTD is. Okay, so as I was telling, so LMTD, that is logarithmic mean temperature difference. Logarithmic mean temperature difference can be explained like this. The definition of LMTD goes on like this. Logarithmic mean temperature difference is defined as that temperature difference which, if constant, that is if it is maintained constant, if it is constant, would give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. So that is what is called as LMTD. So how do we understand this definition? This is what this definition is all about. But I just want to give you an idea about what is this LMTD actually is. See, let us try to consider, no, this is what we are going to do it now. That is logarithmic. Obtain an expression for LMTD for parallel flow heat exchanger. So basically what is happening, this is a parallel flow heat exchanger. We have considered the flow arrangement and the respective graph here. So what is happening here? So the cold fluid is entering, so from left to right. So let us call this as 1 and this as 2. So 1 represents the inlet and 2 represents the outlet. So this side it is inlet and this side it is outlet. So what is happening in heat exchanger, you could see here there are two pipes and there is a hot pipe which is sandwiched between two cold pipes. So that means to say, here blue color indicates the cold flows and the hot indicates, that is the red color indicates the hot fluid. So the temperature of the cold fluid is varying as it moves along the length of the heat exchanger. So this is the length of the heat exchanger. As it moves along the pipe, the temperature of the cold fluid is also varying. Temperature of the hot fluid is also varying. Yes or no? So the temperature of the hot fluid, since it is a hot fluid which will be entering at a very high temperature than the cold fluid, the temperature of the hot fluid will start reducing as it moves along the length of the heat exchanger. The cold fluid, what is going to happen for the cold fluid? For the cold fluid, the temperature of the cold fluid starts increasing as it moves along the length of the heat exchanger. So this is what is going to happen. So now if you see, the temperature is also varying. Here it is also varying. So how the heat transfer is happening? Heat is transferring from hot fluid to cold fluid simultaneously. So if I just want to, so heat is being transferred from hot fluid to the cold fluid. Now there is this temperature difference. Whatever the difference is there, here it will be different, here it will be different, here it will keep on, like it will be varying, because the hot fluid temperature is also varying, cold fluid temperature is also varying. But for the heat transfer to take place, there should be a temperature gradient between the hot fluid and the cold fluid. So that is where we are finding out what is that temperature difference. So if we try to maintain that constant, then what is going to happen? So now I am going to take you to this again definition. So LMTD is defined as that temperature difference which, if constant, would give the same rate of heat transfer as actually occurs under variable conditions of temperature difference. Under variable conditions of temperature difference. So it has to take into account of the heat transfer. That means the temperature difference should take into the account of the variation of cold fluid temperature and the variation of hot fluid temperature, and it should give us that value of temperature difference which we should use it in order to calculate the heat transfer rate. Understood? We cannot try to calculate the heat transfer if we take only at the inlet or at the outlet temperature. It should be somewhere the mean temperature kind of a thing. Okay, so that is what the definition of heat transfer. So now we need to find out, we need to derive the relationship for the logarithmic mean temperature difference. So as this graph also indicates the same thing, you can see the x-axis denotes the length, or you can consider it as an area. So this is what is the length of the heat exchanger or area of the heat exchanger, and your y-axis, that is x-axis, is the length. We'll keep it simple as the length. So your y-axis here, the y-axis represents the temperature. Understood? So you can just see here, this is the hot fluid which is entering at TH1. That is why it is at the top, it is at the higher, and this is what the TC1, which is the low temperature. So as it moves along the length of the heat exchanger, the temperature of the hot fluid is coming down. You just see the TC1. As it moves along the length of the heat exchanger, the cold fluid temperature is increasing compared to its inlet. So you can observe now at the inlet we have one temperature. Let us now that we have denoted as theta1. Temperature difference at the inlet is denoted as theta1, that is nothing but TH1 minus TC1. Similarly, at the outlet we have a temperature difference, that is theta2, which is TH2 minus TC2. Okay, now if we now try to take somewhere a small area in between, this is called as dA, and you can just see here the graph is coming down. Okay, if you want to take the slope, so this difference is what is dTH. So you can just see this is the temperature difference for the hot fluid curve. Similarly, here also there is this slope which is maybe increasing here. This is dTc, and heat is always transferring from hot fluid to the cold fluid. Okay, so this is what the graph and this is what the flow arrangement is. So you can just see the arrow mark here, both are in the same direction. That is why it is called as parallel flow. Parallel flow heat exchanger. This is what the graph for parallel flow heat exchanger. Okay, now let us try to define, or let us try to derive what is the expression for LMTD for the parallel flow. Okay, now let us now start the derivation here. Now let us consider, as I told, let us consider a small elemental area along the length of the heat exchanger. That is, across the length I have considered a small elemental area. Now the rate of flow of heat through this elemental area. So first let us consider an elemental area, an elementary area dA of the heat exchanger. Okay, the rate of flow of heat. Now what is that? The rate of flow of heat through this area is given by, what is that? Now what is happening here? See, the heat is transferring from hot fluid to the cold fluid. If you have considered a small elementary area, so you have a temperature difference, some we don't know that TH, at some point it is TH and it is TC. So what will be that? So basically the flow is HA delta T, correct? Or if you consider here, let me just write it here. What is happening? From the hot fluid to cold fluid, you have a heat transfer coefficient for the hot fluid and you have a heat transfer coefficient for the cold fluid. So, and also it is separated between a small solid wall. Okay. Also, I told you in the introductory class, there is what is this called as fouling factor and all. So, if you consider all those resistances, we may have to consider the overall heat transfer coefficient. So, the dq, that heat transfer is given by what? It is given by U times dA times Th minus Tc. You understood? All those, this U is nothing but overall heat transfer coefficient, which you have already studied in your convection or in the conduction heat transfer analysis. You have, whenever you have a heat transfer happening between two different fluids and are separated by a solid layer, then you need to consider overall heat transfer coefficient. Okay, so dq, the same is happening in heat exchanger, so we need to consider U. With respect to the convective resistance, also you have fouling resistance here, which should be considered while calculating U. So dq is U dA dTh, or in a simplified form you can write it as U into dA into delta T. So let us call this as equation 1. Please mark this equation, numbers are very much required. Okay, so now if you observe here, what is happening, this heat transfer. So as a result of heat transfer dq, through this area small dA, what is happening? See, if you observe here, heat is transferring from hot fluid to cold fluid simultaneously. So at this small area, what is happening? The heat is transferring from hot fluid to the cold fluid, because of which what is happening? The heat is lost by the hot fluid and heat is gained by the cold fluid, or in another way we can put it in this format. So some amount of heat is, like, it is, the hot fluid is cooled and cold fluid is heated upon. Cold fluid is getting heated. Okay, so if you try to put the energy balance, so let us try to write it. The energy balance over a differential area dA is given by, correct? So there is a small heat in this small differential area is transferred from hot fluid to cold fluid, because of which that much amount of heat is lost by the hot fluid, which is equal to the heat gained by the cold fluid. Do you agree with me? Correct. So how do we write this? How do we write this equation? So this dq is equal to what? So heat lost by the hot fluid. Heat lost by the hot fluid means what? Minus comes into picture. So what is the amount of heat that is being lost by the hot fluid? Can you tell? So which is energy balance? If we try to put it, we use that, MCP delta T correlation. Okay, you know that the simple energy balance fundamental, that is Q is equal to MCP delta T. So we'll try to use this M dot H CPH into DTH. So the difference in the hot temperature, that means what is the difference that it is having? So y minus sign, because the heat is lost. So heat transfer from the system is considered as negative. So that is what it is. So which is equal to what? Heat gained by the cold fluid. So M dot C, CPC and DTC, which is nothing but equal to what? This dq, that is nothing but what? U into dA into Th minus Tc. Do you agree with me? So this is what the heat transfer happening. Correct? So now please call this as equation 2. Now let us try to make a small modification in this. So I'll just try to keep this here. So what is going to happen? Now I'll try to, just write it in a different form. How I can write it? So I'll try to write it like this: dth equal to minus dq by m dot h cp h. So by the way, what is this m dot h? Mass flow rate of hot water. What is cph? It is specific heat of hot fluid. Okay, TTH is the temperature, you know. Similarly for the cold fluid. So m dot represents the mass flow rate, kg per second. Always it should be in kg per second. So which is nothing but equal to, you know, this m dot h into cph can be written as heat capacity, which I will be denoting it like this. Capital, just write it as ch. So this capital C denotes m dot h into cph. Okay, please be aware of that. Okay. Next, similarly it is TTC is equal to dq divided by m dot c cpc, which is nothing but dq divided by capital C. Okay, so if you want, you know, let me just try to write it here in this thing, that is m dot h into cph, which is equal to ch, which is called as heat capacity. Heat capacity of hot fluid. Similarly, m dot c cpc, which is cc. Similarly, heat capacity of cold fluid. Okay, are you following? Okay. Next, similarly, what is that we need to do now? Now, let us try to subtract these two equations. Okay, what is going to happen? Now, please call this as, please follow this thing. Equation 1, 2 is there. So, let us call this as equation number 3 and let us call this as equation number 4. Now, let us try to do the subtraction part. That is, you subtract equation 3 and equation 4. So what is that I am going to get? It is dth minus dtc, which is equal to minus, so I am going to write it like this, dq into, please observe here, 1 divided by ch plus 1 by cc. Can I write it like this? Do you agree with me? So already one minus sign is there, so that's why I've written here. So minus comes here. Since we are subtracting equation 3 minus 4, so I'm writing here equation 3 minus equation 4, dth minus dtc. So we shall now call this dth minus dtc as d theta. Okay, let us call this as d theta, which we are going to get it as minus dq into 1 by ch. So this is capital C divided by 1 by cc. Now, if you try to observe here, what is dq? Let me just take you here. The basic definition here, equation 1. Please refer to equation 1. dq is u dA delta t. Correct na? Or th minus tc. Substituting from equation 1, we have for dq that, or substitute from 1, substitute for dq. Therefore, what is that it is going to be? Please write it. d theta is equal to minus u times dA th minus tc times 1 by ch plus 1 by cc. Please call this as okay. Now what is that we will do is, or we shall try to write it in a different format. Since what is d theta? D theta is dth minus dtc, and we have also th minus tc. So theta is nothing but what? th minus tc. So we can write it like this, or d theta. So d theta is equal to minus u dA theta into 1 by ch plus 1 by cc. So very simple thing, you bring this theta down here, this side. Let us try to put it in a more simplified form. D theta by theta is what? Minus u dA times 1 by ch plus 1 by cc. Okay, so what is it we need to do now? Now we have, please call this as equation 5. Now please observe equation 5.